Hey, what's up, guys? I'm Ryan Thaxton. Today I'm going to be doing problem 9.21. Alright, so for problem 9.21, we have to go back to 9.20. So 9.20 is an air standard diesel cycle. Okay, and if we look at a PV diagram for a diesel cycle, we will see actually that's pretty fat. I'll redo that. There we go. This is 1, 2, 3, and 4. Alright, so the first pressure that's given is a P1 equals 95 kilopascals, and P3 equals 7,200 kilopascals. T1 equals 300 Kelvin. T3 equals 2150 Kelvin. And they want us to solve this using the specific heats evaluated at 300 Kelvin. So, what we do first is isentropic ideal gas. Alright. At T equals 300 Kelvin, at T equals 300 Kelvin for air, table A22, K equals 1.4. So now we'll use this equation right here. Solve T2 over T1, which equals. So now I've solved out this. And T2 over T1 equals P2 over P1 times K to the power of K minus 1 over K. And T2 equals 1033 Kelvin. Alright? So now we're going to try to find the volume. More specifically, the specific volume. We're going to use equation 6.44. So, T1 over T2 equals specific volume of V2 or V1 to the power of K. So, V1 or V2, if you do some algebra, you'll find V1 over V2 is equal to 22, which is actually the compression ratio. And also the first thing they want us to find. So that's A. Oops, go down. Next we're going to find the cutoff ratio. So cutoff ratio is V3 or V2. I'm gonna pause it here. Alright, so now we have these values. V3 equals 0.0857 meters cubed per kilogram, and V2 equals 0.04117 meters cubed per kilogram. So now we can find the cutoff ratio. 0.0857 divided by 0.04117, and that will give you 2.081, and this is the cutoff ratio. So RC equals 2.081. That's part B. Now, where are we going? We're going to find the thermal efficiency, N, or eta. For doing that, we're going to use equation, we're going to use equation 6.44, or look on your thermo book on page 503 for an isentropic ideal gas. T4 over T3 equals 3 4 K minus 1. I'm going to solve it out over here and pause the video. Okay, so now that we got everything, so for V3 over V4, for finding V4, if you look at the PV diagram over here, V4 equals V1, alright? And to find V1, well, we already have the temperature, we already have the pressure, so now we can find V1. So what we do a few calculations over here, and we find that V1 equals 0.90663. So now we'll use this equation. T4 over T3 equals V3 over V4 to the power of K minus 1. And if you do a little rearranging, T4 equals 2150 Kelvin times 0.0857 meters cubed per kilogram divided by 0.9063 meters cubed per kilogram to the power of 1.4 minus 1. And that equals 837 Kelvin for T4. Alright, that was a mouthful. So now, we'll find the thermal efficiency. So the thermal efficiency eta equals Cp times T3 minus T2 minus Cv times T4 minus T1 divided by Cp times T3 minus T2. Now if you look at table A22, you'll find Cp at 300 Kelvin for air equals 1.005 Cv equals 0.718. Alright, so now if you look at this, we can do some algebra here. Reduce it a bit. Do 1 minus CV over CP times T4 minus T1. Oops, T1 divided by T3 minus T2. Alright, so that equals 1 minus 1.005 divided by 0.718. And also keep in mind, CV divided by CP is also 1 over K. And we already have 1 over K, it's 1.4. Right? So we could do that too. Alright, let's back to it. T4, 837 minus 300 Kelvin, T1, divided by 2150, which is T3, minus 1033, which is T2. And you will get an efficiency of 65.7%. And there's your answer. Part C. Alright, moving on. So now the final thing that we have to find, the mean effective pressure. Mean effective pressure, we're going to do MEP equals work net over displacement volume, which in this case can be V1 minus V2. And that equals CP times T3 minus T2 minus CV times T4 minus T1 divided by specific volume of 1 minus specific volume of 2. And we will get 0.005 times 2150 minus 1033 minus 17. So if you use your calculator, calculate all of that, the mean effective pressure, is 852 kilonewtons per meter squared, right? Because this is meters cubed per kilogram, and this is. And so now, if you do all this, you do a little bit of unit work, then you'll find that MEP doing all this is actually kilonewtons per meter squared, which is, of course, kilopascals, which is what you're looking for. So the mean effective pressure is 852 kilopascals. Alright. Also, I made an error up here. Just to let you know. It's table A20, not A22. Alright, guys.